All right, hey everybody. I'm so sorry about not being there today. My son is sick. But I'm gonna do what I can. I think it's funny. I cursed myself as soon as I said that we wouldn't go over anything. There wouldn't be anything on the exam that we didn't go over in class, because there will definitely be things that we're gonna go over right now, but I will try to make it quick, but also make it very relevant to the exam so that you guys know what to study. So, all right, let's start with enthalpy real quick. We've talked about it a little bit in lab, so this is a bit of a review. But remember that we look at heat as we look at enthalpy as kind of like heat, right? And we denote it with an H. So if you have a reaction, let's say that this is the reaction coordinate, meaning this is like the reaction progress, so reaction coordinate, or sometimes you'll see people write reaction progress. Okay. So as the reaction occurs, any A plus B going to C kind of a thing. What's going to happen is you'll start at a certain energy level, and over here your y-axis is energy. Start at a certain energy level. And if you go up and you end at a lower energy level than you started with, that means you started with a certain amount of heat and you let heat out. This would be an exothermic reaction. Again, that's because you ended lower than when you started. Okay. So this would be like anytime you burn something or anytime heat is released. So an exothermic reaction is a kind of reaction where you actually feel the heat. So the surroundings get hotter, but the reaction itself, notice, got cooler. That's because it let heat out. Okay. Then if we do the opposite over here, again, we'll write, I'm just going to put RxTN for reaction. Coordinate, and over here was energy. And for any other reaction, like A plus B yielding C, doesn't matter. So this represents any reaction. If there's a reaction that starts here and ends up higher in the reaction diagram, this up here, that means it took heat in. This would be a delta H equals positive. In other words, an endothermic reaction. Okay. The reaction, so the one that I'm thinking of automatically that's an endothermic reaction would be like baking soda and vinegar. When you feel it, it's actually cold if you mix baking soda and vinegar together. It feels cold because the reaction itself took the heat away from your hand, and that's why it would be endothermic. Now, one thing we didn't talk about is why we have a hump here, and this hump varies. Sometimes it's higher, sometimes it's lower, but we call this thing the activation energy. It's the amount of energy required, so it's like the peak up here going down to here. That's also the activation energy. It's the amount of energy that's required for a reaction to occur. So for example, let's say you want to start your barbecue fire and you have propane and you have oxygen, right? So you should technically have a fire, but you need to do something in order to get that fire going. What you need to do is add a spark, right? You need to add a certain amount of activation energy, so that allows the bonds to start breaking, and then it can start releasing heat. So it actually oftentimes requires a certain amount of heat in order for it to occur. Okay. So this would be considered the activation energy. Now what you guys need to know is essentially that this is the activation energy from where you start to the peak of this hump. From where you start to the peak of this hump, and I could draw a better hump, let's say it's like that, okay, would be the activation energy. The other things you need to know, that if you start here and end up lower, it's exothermic. If you start here and end up higher, it's endothermic. You also need to understand this one would feel hot, right, to the touch. This one would feel cold to the touch, and understand the differences in those. All right. That was the main thing I wanted to go over. So let's go ahead and keep going. We're gonna talk about different enthalpies. I'm gonna give my dog a bone because he gets one when I'm filming a video. Okay, take them all, dogs. My dog just got 80 bones. Okay, so enthalpy of a reaction. So this is the enthalpy that's produced or given off by a reaction. We have already talked about this. This is like when you have some kind of A plus B yielding C thing, and then we always put the delta H of the RXN, that's the reaction, over here, and it's going to equal whatever it equals, okay? This is always going to be in just plain old kilojoules, okay? This is the enthalpy. So we use this when we did stoichiometry. So let's say, for example, this was 2A and 3B and 4C, and this was 100 kilojoules. So for example, we would say for every 2A and 3B, you require 100 joules to get 4C. Okay, so we use this in stoichiometry. And just to really drive this point home, let's make up a question real quick. Let's say, how many kilojoules are required to make, let's say, 8 mole of C? You might be able to do this already. You know, to make 4 mole of C, you require 100. So to make 8 mole is 200. But even if we didn't, let's talk about how we go about doing this. This down here would be 8 mole, and this would be our question mark. Okay, so we'd start by saying we have 8 mole of C. We know for every 4 mole of C, it requires 100 kilojoules. And you'd get 8 divided by 4 is 2, times that would be 200 kilojoules. So when we use our enthalpy of reaction, we often use it in stoichiometry. We also use it in Hess's law. So if you remember when we manipulate equations, multiply them, divide them, etc., and then add them up, that is also when we use it. So using stoichiometry and Hess. Let's look at the enthalpy of formation. This is the enthalpy that's given off by the formation of a compound or an element. So this is delta HF, where the little f stands for formation. The units of this are in kilojoules per mole, and we're going to be working with it right now. Before we do, let's go over a few things. So on the periodic table, there is an N, an O, an F, Cl, Br, and I, and there is also a hydrogen. These are all diatomic things, meaning in nature, they actually exist as twos. And it's important to know these when we talk about the enthalpy of formation here. Everything else usually exists as ones. There is SEP and S here, where the S's oftentimes exist as 8s and the P exists as 4s, but sometimes this can change depending on the context, okay? So the most important thing that we're going to be talking about, and I know for a fact that these don't come up, are these. They make a number 7 plus the hydrogen. So there are 7 of them, and they make a number 7 plus the hydrogen. Okay. Why these are important is because these all have delta H of formation equaling to 0. In fact, anything in its elemental state, and that would be kilojoules per mole, has an enthalpy of formation of 0. So for example, if you have O2, its delta H formation is 0. If you have anything else that's a monoatomic, carbon, iron, lead, copper, all of these, the delta H of formation equals 0. Same for this, that, and that, okay? Every single one of them, the delta H of formation equals 0. So, we've already kind of talked about what that means, but let me give you an example. Let's say you have something like you want to form sodium nitrate. Okay. So sodium nitrate didn't just spontaneously form in the world, right? It came from other things, if that makes sense. And so in order for it to come from other things, we have to talk about what those things are. Now, in the past, we've broken this down into a sodium and a nitrate because we talked about them being soluble, et cetera, et cetera. But here we're looking at breaking down things in their elemental form. Again, we already did this in class, but this is just a reminder. So this sodium nitrate was made out of sodium, nitrogen, and oxygen, right? So we would say that we started off with sodium. Sodium's a solid. Nitrogen, which we know is diatomic, so we got to write N2, and oxygen. Okay, I'm going to write it bigger here because I won't be able to balance it very well. So I'm going to write it down here, sodium plus N2 plus O2, yielding NaNO3. Okay, so now you balance it, but you want to keep this as 1. This is that one time where we balance it and we go ahead and we use fractions, right? So if there's 1 sodium, there's 1 sodium. If there's 1 nitrogen over here, you have to find a way to get 1 nitrogen over here. So in order to do that, you would have to say 1/2. Okay? That gives you 1, because 1/2 of 2 is just 1. And then the O2, you'd say 3/2. If that's confusing to you, just always take the number that's here, put it on top, divide it by 2, and you'll always get the right answer. So this happened to be 5, you would put 5/2 here. All right, and this is a balanced reaction now, and this would be the formation reaction. Of NaNO3. Why is that? Well, because it started off with everything that's elemental states. Sodium, nitrogen, and oxygen all combined to give us sodium nitrate. Okay. This would be a delta H in kilojoules per mole. And I wish I knew the number right offhand. I don't, but we'll do an example here in a second where I show you kind of how everything works. All right, so the important thing to think about for these is, again, you just want everything in the elemental state. And you want to have it forming 1 mole of the thing that you're interested in, which in this case was sodium nitrate. So everything in this elemental state, and it's got to form 1 mole of that. All right, let's go ahead and use it, shall we? And I didn't do this in advance, which is good, so I'll do it all in the calculator for you so you can see. All right, so you find enthalpy of a reaction. You can find enthalpy of a reaction when you're given the enthalpy of formation and vice versa. Okay. So here, it's asking you to find the enthalpy of a reaction, meaning 4 moles of this and 5 moles of this, yields 4 moles of that, 6 moles of that, and some delta H of the reaction. And it gives you the enthalpy of formation, meaning the amount of enthalpy it took to form NH3, the amount of enthalpy it took to form O, the amount of enthalpy it took to form NO, and the amount of enthalpy it took to form gaseous water. Notice this is gaseous water. Sometimes you might be given liquid or something to that effect, so it's good to pay attention to those states. So it wants you to figure out the enthalpy of the reaction. One important note here is that, remember, anything in its elemental state, its formation enthalpy is equal to 0. Okay, I foresee myself asking a question like that on the exam. So make sure you know anything, all the diatomics, anything monoatomic are all going to equal 0. All right, so here's how we do this. Well, real quick, just to make sure we're on the same page. When I say the enthalpy of formation, I'm talking about in order to form 1 mole of this, it lost 45.9 kilojoules for NH3. Okay. So when we go up here, what we're going to do is simply plug it in. If it's that much enthalpy for 1 mole, and up here we have 4 moles, we just say 4 times negative 45.9. We're going to split this into 2 parts. Okay, we'll have the product side and the reactant side. Over here we have plus 5, but that happens to be 0. Here we have 4, and for the NO, it's 90.3 kilojoules per mole. And then over here, plus 6 times the gaseous water, which is negative 241.8. I'm going to go slowly here to make sure that we're all on the same page. So what we're going to do is we're going to add up everything on this side and add up everything on this side. And then we'll talk what to do after. So 4 times negative 45.9 equals, and I get negative 183.6. And then this would be 0. Negative 183.6 plus 0. And everything on this side has a total of negative 183.6. Okay, and that would now be kilojoules. Why kilojoules? Because this was 4 mole times negative 45.9 kilojoules per mole. Moles canceled, and we're left now with just kilojoules, which is good because our delta H reaction has to be in kilojoules. Stop my dogs from stealing something. Okay, so now let's go to this side. 4 times 90.3. I get 361.2 plus 6 times negative 241.8 gives me negative 1450.8. And now I will just add them up. And I get negative 1089.6 on this side. Okay. And again, that's kilojoules. Now it wants us to find the delta H of the reaction. That was our whole thing that we're trying to find. So in order to find that, all we do is take the products minus the reactants. Remember, the final thing minus the initial thing gives us a delta. So delta H equals products minus reactants. In other words, negative 1089.6 kilojoules minus a negative 183.6 kilojoules. Remember, when you subtract, it's the same thing as adding a positive. So I'm just going to take the number that I have here and I'm going to add 183.6 to it. And I get an answer of negative 906.0 kilojoules. Cool. So again, all we do is take the moles that we have, multiply it by the enthalpy of formation, which will be given, always. If it's not given, ask yourself, is it possibly 0? Because if it's in a standard state, this oxygen, I didn't have to give that to you, if that makes sense. Okay, we add them up, and then you take the product side minus the reactant side, and that gives you your answer. In other words, if I did this reaction, it would lose 906 kilojoules of heat for every 4 moles of that and 5 moles of that I had. All right, moving on to the last little bit. Let's take that same thing and pretend we didn't know what we just learned. So if we didn't know that information, this should be 906.0, because sig figs. Come on, gold. Okay, so let's go ahead and do this reaction now, but a little bit backwards, if that makes sense. So now it's saying, hey, you've got this, this, and this, and it says, but hey, what's NH3s? Well, we know that 4 NH3 plus 5 O2 yields 4 NO plus 6 H2O. And we pay attention to the fact that that's gaseous because that gives us this number here. And we know that the delta H of that equals negative 906.0. We already know that if we added up everything over here and added up everything over here, products minus reactants would give us this number. So let's go ahead and split it up a little bit, but this time do something slightly different. Okay. We know that this one is what we're trying to solve, right? So instead of saying 4, we're just going to say 4 times x, okay, instead of using the number that we have there. Plus 5 times 0. Okay. Over here, again, we have the 4 times the 90.3 plus the 6 times the negative 241.8. We already did those on the previous page, if you remember, and we figured out that this was negative 1089.6 kilojoules. And over here, if we added everything up, this would be 0, so we just get 4x. We know we take products minus reactants gives us the delta H overall. In other words, negative 1089.6 minus 4 times x equals negative 906.0. All these have units of kilojoules. Our goal is to get x alone. Okay? So what we're going to do is take 906 and we're going to add to it 0.10 or 1089.6 to both sides. And that tells me that negative 4x equals 183.6. Now we just divide each side by negative 4. And that cancels out the 4's. And I find x equals negative 45.9 kilojoules, which is fantastic because that was what we got on the previous page. Okay. So know how to solve for unknown ones and know how to solve for the enthalpy of formation or for the enthalpy of the reaction when you are given the enthalpy of formation. Also remember that anything in its elemental state is equal to 0. All right, crew, there's an updated topic list for you, which is right here. Just let me know if you have any questions on it. Remember, this is heat and that's work. Go back and study the first one we did in the first lecture we did for chapter 9. Q equals MCAT, Q equals MCAT, endo versus exothermic reactions. I tried to keep some very simple questions in there, so make sure you know the graphs though as well that we just learned. Stoichiometry and enthalpy, a lot of stuff that we did in class already. Everything's things that we did in class already with the exception of what we just learned today. Let's see, things we learned today, recognize things in their standard state. Okay, using the enthalpy of formations to calculate the enthalpy of a reaction, using enthalpy of formation to calculate the enthalpy of a reaction, and knowing things that are in their standard state, and how to make formation reactions, which we kind of already did before, but that way you can make sure that you really got it. So you can see for the most part, I tried to stick with things that we've done already, and yeah, study hard. Please let me know if you got questions. I'm happy to make you a video to go over anything, and have a great day. Bye.